Thank you so much, everybody. Glad you're all here. Thank you for joining me. So I'm excited to talk to you about this topic. The question of detecting fraud is obviously an interesting one, and you're all here because it's sort of an unsolved one, right? So I'll share some experience with you regarding this topic. So what I want to bring up first is the idea of how fraud detection is typically done. So we'll talk about the legacy fraud detection system, and then how I've experienced going from that legacy detection system to converting it to machine learning and utilizing all of the power of Spark and machine learning that we're all talking about this week. How to improve our model, how to keep going. That's a really important piece of fraud detection because it's constantly changing, right? So fraud, as soon as you detect it, it starts to, people who are doing the fraud are going to start doing more things, different things, and how that solution was applied in Spark. So this is something I did at a previous company, but this is kind of generalized, hopefully for everyone's use case. And I'll show you a little bit with how you can put some models in a Spark pipeline and track with MLflow as well. So in a legacy detection system, what we're kind of used to seeing is that we have different business units working on very separate parts, and so their data is siloed somewhere in different, probably on-prem, servers, and then to go to deploy it, that you're limited in how you deploy that kind of solution depending on what your server supports. So in my experience, it was SQL, right? So if you have, the three different components, you have the data engineer, the analyst. This is usually the person who is the business user who understands fraud, who can tell you what rules to apply, right? How to find this this thing that we're all looking for. And then the data scientist is kind of the go-between between the data engineer and the data analyst, but they're the ones building the models. And so what typically happens, right? So you have this business user who kind of says, well, this is what we're looking for. And they have data scientists who is working typically with subsample data, right? So you have some data somewhere. The data engineer hands over some sample of the data to the data scientist. The data scientist goes and builds a model, typically in R or Python, right? And then goes back to the data analyst, says, how does it look? Data analyst says, okay, sure, right? And then the data engineer gets this model and says, well, I can't deploy R or Python in our system, right? So I need to translate it into something. And that's and that becomes some sort of convoluted thing that's typically a rule-based system, right? So the rule-based model is sometimes it's derived directly from the business users when there's no data scientist present, and sometimes it's literally, here's an R model, maybe a linear model or something like that, right? And then, okay, let's use the thresholds of this model to convert them to some SQL query. And so the where clause of the SQL query is what's going to be the model. And I've experienced this, so I'm hoping this is resonating with you as well. Because how else, right? How else do we kind of implement the knowledge of the domain experts in the field, right? We put them in some sort of system and whatever the language is that you're able to deploy. So typically there's some business knowledge that gets transferred using, some really long SQL query, which is kind of scary because it gets really brittle. And if you want to change any part of it, if you want to change a threshold, right, all of your code breaks. And when that happens, right, that literally prevents you from keeping up with new patterns of fraud, right? You literally can't. We discovered a new type of market manipulation in the U.S. stock markets, and we want to put it in production right away. Well, given the code base, we can't because it's so brittle, right? That is it takes like a year from development to go to production, right? So we want to obviously make it all faster, right? So when we're dealing with constantly changing fraudulent behaviors, we want to make all of this faster. And so that's where, for me, really Spark comes in. It's a unified system. So all of those, the data engineer, the data scientist, and the business user, they can all work on top of it, right, in different kind of parts, But really, they can have all of them. All of the domains can have access to directly to the data. And once you have access directly to the data, that means you can model directly on at scale on real data, and then you can deploy it on that same system. So that's really to me the one of the missing pieces here. Right. So as far as the machine learning component, so we have a rule-based model. And that rule-based model has been likely producing some success, and it's been kind of working for the business for some time. So let's assume that's an assumption, but let's assume that that's a model that works for us. Okay, so given that we are somewhat happy with that rule-based model, we're going to train our first machine learning model directly on the labels that are the output of the rule-based model. So that's just us converting. We already have existing rules. We have the features. The features are going to be the inputs into the rule-based system. Sorry, my mouse isn't working. There we go. So that will be our first machine learning model. That's a pretty straightforward conversion. And so the reason why I like it is because we already have everything we need to get started with machine learning. The reason why it's going to be better for us is because we can then update our model as new fraud comes in. We can update our labels easily. We can retrain and redeploy. And it could be quite fast, right? And with the power of Spark, this is done at scale, right? And so the data scientist is working directly on the model that's going to go into production, and the data engineer is responsible for deploying it at scale, right? And so that's really the nice first step. And the reason why we kind of use, so in my previous career, that was the biggest problem really, was convincing the business user that we can go away from the rule-based system to the machine learning system. And the machine learning they were like, well, that's going to take my job, the things that you probably hear often. And having a pretty simple model that's easy to explain was a nice first step to get them on board. And so I'll show you a little bit in my demo. And really, the big sell is that this model is going to find new cases. So first of all, of course, our rule-based system has a lot of false positives. We kind of know that, but we've already accepted it as it's been in production for a long time. So we are guaranteed to be modeling existing false positives, right? So we know that, but we've kind of said, okay, this new model is probably going to give us more false positives. And the way to think about it, or the way I've been thinking about it, is that really it's giving us more data on new kind of maybe unseen fraud patterns, because the hard set thresholds that are part of our rule set are giving us only what we set. But this machine learning model may potentially discover new things, but we do want a system that comes back and provides a feedback loop in terms of updating the labels. You really can't, you can't assume that the machine learning model is giving you a complete picture, just like the rule-based model is not giving you a complete picture, right? So we need some sort of a feedback loop in place to update our labels. That's really the thing that kind of no one thinks about when they first start. They're like, okay, model. We got the model deployed, we're in. But really, how do you live with that model going forward? How do you update it? How do you feedback? So what kind of results do you provide to your human business users, right? So the model output is going to be in the billions of records, probably, right? And it's going to be flagging, at least hundreds, thousands, millions of cases. Which cases do you show to verify, to validate, right? So in a credit risk model, you're going maybe even live, right? In my experience in financial fraud, you're identifying market manipulation, which is happening all the time. Well, to a degree, and hopefully, and you need to come back and update and say, well, this was actually the model flagged market manipulation. This is actually true market manipulation, and we tell the model that yes, it's correct, or no, it's not correct. Obviously, we want to know that. We want to keep track of that. That requires a kind of a separate component. So, like I said, we're going to be dealing with a lot of false positives, but we're going to also introduce some uncertainty, some extreme cases. So what I mean by extreme cases is, for example, a model is really sure that this is fraud, and then you have the business user look at it, look at the result, and say, no, it's not. So we want to put that back in as a feedback, part of the feedback loop. The opposite scenario is even worse. The model is sure it's not fraud, and then the business user says, actually, it is. So how do we deal with that? So one way that we've dealt with it in the past is put that record back in, update the record. So this is actually with Delta Lake, right? This is actually pretty straightforward to do. So you're updating the record with a new label of your model. And you also might want to derive some new features that will highlight that use case better. So that actually is where the data scientist really comes in, working with the business user to update not just labels, but also maybe the features, and possibly reweight and retrain the model. And as far as selecting the appropriate model, there are so many questions here. And I'll show you some code and kind of give you my way of thinking about it. But first question is, how accurate do we want the model? So do we want a little bit more nebulous in terms of discovering new fraudulent patterns, right? If as a start, if it's not really production and we're just doing some exploration, or are we looking to make it exactly like the rule-based model just to start and then going forward? Also really important, false positives versus false negatives. That's how false negatives means that the model incorrectly said this is not fraud, right? So this is fraud. The model says it's not fraud. That's not true, and that's really bad because we're missing fraud that we've detected in the past, right? We don't want that. But false positives could be good, could be too many, right? There could be too many false positives, but false positives could be a good thing. So basically the model says this is possibly fraud. We don't think it is, but hey, at least it's flagging something kind of that doesn't look good. We're going to be dealing, another question is, how interpretable should our model be? So this is really, there's a couple of parts to this. Obviously for our understanding of what the model is doing, but really if you're in the financial world, you have to be audited, you have to explain this model to people, and if you're flagging individuals, you have to have a reason. Why did I flag you as doing credit card fraud, right? Why am I declining your transactions? You want to be able to explain this. Again, at the very beginning, when you're selling this model to stakeholders, you have to be able to explain it, because they're saying, well, I had this rule set that I was comfortable with, and here you are with your black box model, right? So we know that models are not black box, but how do you show that? How do you show that the model did its job and flagged everything correctly? How do you prove that, right? And finally, you're definitely going to be dealing with class imbalance, because hopefully there's not that many cases of fraud, right? That's good, but that means you're dealing with a very imbalanced data set. So that's a factor as well when you're training. And so as far as a pipeline, so obviously Spark Summit, but I think Spark is the answer here, because we're working with the data at scale, and doing your data manipulation and preparation on Spark it's a fantastic tool to get it ready for the modeling piece. And then the question is which model to use, right? But you can stay on Spark to do all of that, and I'll show you some models that I've used. I'm a fan of the sparkling water models, which are H2O models that have a wrapper that you can run them on Spark. So they're quite good, and they give you all of the options that the H2O models give you outside of Spark, right? So just using the sparkling water wrapper, which is quite easy, will give you all the power of the H2O models. And then all of that is really easy to deploy in the Spark pipeline and track with MLflow. And so as you guys know, tracking with MLflow allows you to also save the model object and then easily deploy it. So quite nice. Let me show you this demo here. Okay. So here's some code. And I'm running, this is a local instance of Spark. Just wanted to make sure I'm running locally for the demo here. But, very typical start to this is, and I turn on MLflow right away, but here I read in some Spark data frame. And this kind of is meant to represent some sort of rule-based system. So this is where, if you have a legacy system, let this be sort of a representation of that rule-based system that defines some set of rules. So there's going to be some threshold, right, that says if this and that, this is a yes. So we're given a 1 and we call it label. So this is our label. And whatever went into this model, right? So there's going to be some columns that were used in this rule-based models. Those are our features. So that's our starting point. And so here's the schema of the data frame. By the way, I'm using I didn't put this up here. I'm using a simulated data frame, but it is a data set from Kaggle that is ATM transaction fraud. So it's a pretty good data set if you want to play around with fraud. And it is in balance, and it has all of the components of a real data set. So it's a pretty good one to try. And it's fairly good size too. So so I created the label myself. In the Kaggle data set, it has a true label, but again, it's simulated. So because we really don't have a well-labeled data set that is fraud, right? So that's my point, that we are inevitably relying on some rules that were set by someone at some point, all right? So all of this is just using Spark to manipulate the data to prepare it for the training. And, doing the checks. Do I have any nulls in the data set? No. And here's my... So from what I flagged, here is the number of fraud cases. So it's about 4%. So that's just based on the rules that I created of all cases, right? So it's still, we expect it to be quite imbalanced. And splitting my data. So just still in Spark, using the first model that I'm going to try is using a Spark ML decision tree. And in my experience, using a decision tree and showing it to stakeholders has been really powerful to show them that machine learning models are not necessarily black box models, are really easy to explain, right? And that's been a win. And this is just kind of sharing, how does a data scientist talk to a business user? Sometimes you show them something that's not, you want to be you want to be fancy with your models. Sometimes you show them something that's really straightforward. They really kind of buy in and then become your biggest champion in the organization. So that's something that is so simple. But you show them this decision tree, and then they see that the rules that they've been working on for 28 years, right, to detect this type of fraud, are being recovered by this machine learning model without it having any knowledge of what fraud is, right? So it's kind of recreating that rule-based system. So that's actually a powerful tool. And so, you show them literally, here are the rules, and here's how the decision tree came up with it. It's quite nice. But the problem with decision tree models and why they don't come to the forefront of a data scientist, right, is because they're not necessarily very good. So one thing I can guarantee, if you're doing the setup like I'm talking about, which is using rule-based labels and features and putting a decision tree on top, you're going to get results like this. So I'm tracking here, AUC, precision recall, F1 statistics. You're going to have good results. And as you can see, these are very high, right? But that's expected for two reasons. One, I'm literally recovering existing rules and features, and the other one, I do have imbalanced data, right? So I'm kind of expecting these to be high. Just as a start, I'm showing you this. But what I really want to know is the model that I live with, it's going to give me some false positives and false negatives. So this is the confusion matrix of my test set. This is what I actually care about. And outside of all of these model metrics, this is really what kind of shows you how you're going to be, how many false cases are you going to have to be dealing with, right? Misclassifications, etc. So this is kind of a look. I like confusion matrices. By the way, though, this really depends on what threshold you set. So the default is 0.5, so I'm not messing with that yet, but it is obviously changeable. But the default model gave me quite a large number of false negatives and no false positives. So this is my true label, this is my prediction, right? So this is the false negative rate. quite a lot. I'm going to have 1,000 cases that are misclassified by the model, and basically it goes as I used to recognize this as fraud. I no longer recognize this as fraud. So not good. Want to do something else, right? So I want to, and here I can either tune the model at this point. So a couple of options, right? I tune the model at this point. I try a balanced data set, which I'm going to do, or I start playing with the threshold that's giving me this confusion matrix, right? So I'm at 0.5 right now. If I move it, it's going to give me a different looking confusion matrix. Maybe that will do it, right? So there's a couple options there. And remembering to track it with MLflow, which I'll show you in a second. So balancing the classes, I get to a different result, but it doesn't seem to have, it kind of made the model a little bit worse. It misclassified more cases. I don't necessarily want to do that. So, you know, this is just kind of my thought process that I'm showing you, and how I would do it and how I would keep track of it. So balancing the classes with a decision tree maybe wasn't the best solution. So now I'm going to start looking at different models. So I'm looking here at a gradient boosted tree model from SparkML. So this one minimizes log loss. That's the default, and I believe the only option in SparkML. And I'm looking here, and again, as soon as you leave the decision tree world, which you should, you're going to have a more complex model. And that complex model is harder to explain. So we'll talk about what to do about that later. But, you know, the model becomes better, and it gives me a better looking confusion matrix. Okay. So I still have a lot of false negatives, but still maybe too much. So this is the point where I'll introduce the sparkling water options. So sparkling water, using the internal backend, all you have to do is create a sparkling water context, so an H2O context inside of your Spark cluster. And so all it's going to do is it's going to allocate some part of your executors to an H2O cluster. And that's so you're going to be sharing. So you're on top of a Spark cluster, you're sharing some part of the Spark cluster with H2O, and H2O is then optimizing the H2O cluster to run its models. So really, all of that is done here. That's it, right? So all I'm doing is creating an H2O context, and that's it. And that creates my my H2O cluster inside my Spark cluster. That's why we call it the internal backend. Quite easy to do. One thing to keep in mind if you're having, so my opinion, if you're running this, doing modeling on Spark clusters, you should not have auto scaling enabled, right? Because you know it's going to be kind of computationally intensive. So this would not, because you're essentially allocating some resources to H2O, you don't want to have auto scaling enabled here. But anyway, that's beside the point. Once you connect to the H2O cluster, you also get what's called H2O flow, which I'll show you in a second, which is a user interface. So at this point, everything that you get with H2O models on your local machine, you get on your Spark cluster. And I think that's quite powerful. So it's basically like if you think about in scikit-learn models, if you're running them on your local machine and you try to put them on a Spark cluster, they don't distribute, but the H2O models do. So I'm a fan. So here we start with, now there's a couple of options here, but I'll show you this one. I'm going to try an H2O gradient boosted model. And the gradient boosted model from H2O, this is a sparkling water wrapper. So I'm still using a Spark data frame. And so I literally didn't have to do anything else. I'm still using a Spark data frame. One thing that is kind of difference between the SparkML models and the H2O models. In SparkML, you have to explicitly say how you want to featureize your data. So if you have categorical variables, you have to explicitly say what you want them to do with it. The H2O models have some built-in defaults, but that handle missing data and that handle all kinds of categorical data or whatever they need to do to convert the data that you give it to data for modeling. Basically a numeric matrix. But there's a bunch of features that you can set. One thing I'm going to draw your attention to here, and this is quite a nice feature, I'm just going to turn this with detailed prediction turn to true. Show you what that does in a second. So here I trained my model, again, still using a Spark data frame, so I did not leave Spark. None of this presentation does. We're all on Spark here. And the model becomes a little bit better. Again, I'm not doing a grid search yet. These are just default models right now. So my false negative rate went down quite a lot, and got some false positives, which I actually kind of want. Again, going to try some balanced data now. So I'm, this is just me trying things, and I'm keeping track of all of that in MLflow because, I may not remember in a couple of days what I did. So I'm just making sure I keep track of it here. Tried the balanced version of the gradient boosted model. It became better in terms of the false negatives yet again. Again, something that I'm concerned about. Again, this is just to draw your attention here. I'm using 0.5 as the threshold just so I directly compare to SparkML. Something that H2O does not do is actually impose a threshold on you. You kind of have to set it yourself because you should set your threshold with some knowledge of the domain that you're in and the use case that you're dealing with. So 0.5 is fine for now. Right. And then one more thing I want to show you is I tried an XGBoost model as well. So XGBoost is a popular model that's kind of known to do really well. H2O has a wrapper for it, so you can run it quite easily with H2O. Again, still on top of Spark. So all I have to do is call H2O XGBoost. Running on my balanced data set, let's see what happens. This is the final model, I promise. I'm making a point here. So after running the XGBoost model, I get to a place where I'm happy. And so I have no false negatives, only false positives, quite a low number. So quite a good model, basically as good as a model probably will get. Maybe with some tuning we can do better. So I tracked all of these with MLflow. So let me show you that. So here are all the models, and I chose to keep track of my test and train metrics. I like to do that just to verify that I'm not overfitting, right? Of course, like if you think about which world we're in, we're fitting to a rule set. So of course we're overfitting, okay? But this is our starting point. This is what we want. Okay, so go with me on this. But between the test and train sets, we're not overfitting. So we're doing quite well in terms of those metrics, and we're kind of this is in order of what I showed you. So the original decision tree, the balanced one, the gradient boosted tree, and then so on until XGBoost. And these are rounded, obviously. They're not perfect models, but they're quite close. And this is the false negative rate that I care about. Nice thing about MLflow is that it's going to show you a picture of all of that, right? So here's my, I don't know if you guys had a chance to play with MLflow, but it works anywhere. It's an open source one, right? So this is running locally for me, but if you're on, again, because I'm using Spark on my local, but wherever you are, you can run MLflow, and it's quite nice to show you, right? So here we have, the models. It gives you all of the metrics that you tracked, and gives you a nice picture to go along with it if you're comparing. Let's see. Let's go with AUC test, right? So the AUC gets higher. So I kind of showed you all of that with the code, but this is something that, if you use MLflow within that kind of experimentation, you still have this to go back to, right? And the nice thing is, when you click on any of these models, if you save the model object, then you immediately have, okay, so I'm choosing XGBoost. Click on the model, and then you have your model object, right? So you can go back here. And here's my model that I can download and deploy, right? So after all that experimentation, I go back and I choose the model. And again, the nice thing is, this is an H2O XGBoost model that behaves exactly, because of the sparkling water wrapper, it behaves exactly like a Spark model, so you can deploy it within a Spark pipeline. So that's pretty nice. So if you're using Spark ML for something else, maybe some feature prep for your NLP use case or something like that, this will work inside the Spark pipeline. And again, here's your model. right? So quite nice. The other portion I wanted to show you here is that when I run my H2O models, I remember I showed you with detailed prediction column turned to true. What it actually does, and this is kind of partially solves my dilemma of how to make an interpretable model, it actually creates Shapley values and exposes them for every row and every feature that you have in your model. So Shapley values are basically contributions of the features to your decision, a yes or no classification, right? And so this is, if packaged correctly for a business user, this could be quite powerful in explaining your model as well. So this is kind of a nice, almost free, slightly computational benefit of running just turning this to true, and then you have your Shapley values. And it doesn't quite look nice, but just so you know, right? So you have for each feature, you have a Shapley value, and the last number here is the bias term. And this is for each row. So you can aggregate it to give you Shapley values of the variable importance and so on. So one final piece, when I'm running this, as I showed you earlier here, when I'm running my H2O cluster, just an added benefit is that you get the H2O flow UI. It just immediately gives you a link to it, you click it. And all of the models that I trained using the sparkling water wrapper end up here. So these are the two GBM models and the XGBoost model that I trained. My data frames are also kept track of here. So you can see that I'm in Spark because I'm using RDD. That's not actually RDD. My models are data frames. That's just giving it a name. But basically now you can actually leave your Jupyter notebook and you can use this UI to train and predict models as well. Just as an aside. So this is another tool for experimentation, right? So if I click this data frame, this is my test set. Here are my features, so on. The other one you can say, I want to use one of the models that I've trained to predict on this data frame, right? This is actually a nice tool for just literally experimenting outside of having to, write a bunch of code just to try things out. One last thing, I'm showing you this to kind of show you the all the options that the H2O models have. So here are the models. So for example, for the gradient boosted tree model, you set your training and test data frames, set your columns, etc. So you can turn off columns that shouldn't be there, and so on. One thing that kind of for this is really actually quite useful for imbalanced data sets. So either we for sure are dealing with imbalanced data and fraud detection. Either I set my data to a balanced data set, so that means that I'm going to downsample my no cases, and I have to be smart about it. So you saw that the decision trees that were fit to balanced data did actually worse because I may be potentially losing some information. So typically these kind of gradient boosted models, XGBoost, they're going to be fitting. They're going to have a stopping metric. The automatic stopping metric is log loss, right? But you might choose a different stopping metric. And so here are all the options that you kind of get in this model, if you guys can see here. And you can even do it, so if you just click this button here, it's going to do it as a grid search. So you might experiment with different stopping metrics, for example. If you're dealing with an imbalanced data set and you run this model, log loss is a good stopping metric for imbalanced data because you're being penalized for being wrong, right? That's the essence of log loss. You are penalized for being wrong. But if you want to add something else into the mix, there you have other options. All right, and so on. So there's quite a few options that you can play with, and this is a nice visual to do it. So I'll leave you with that and go back to my slides here. So 1 second. Play from current slide. All right. So really, this is my final slide. What I wanted to come and talk to you here today about was that really being on the Spark platform is a fantastic way to unify everybody together, right? So the data engineer and the data scientist, that's been my experience throughout. The data scientist and the data engineer are now working on the same platform, and the model deployment is, becomes a breeze. And you don't have a data engineer trying to translate the model results into something. I really think that you're going to get really high accuracy at first from literally converting your rule-based model to ML. And from there, you can really build using a feedback loop and trying to update your models to really fit the real world fraud that you're detecting in real time. Right? That's a really important component. You can make your machine learning models adapt to that, right? So that's the active learning piece. And then the sparkling water wrapper, it really gives you some transparency into the model. So it's gonna do that fine line dance that we're all kind of dancing. Is I want an interpretable model and I want an accurate model. I want both. So it attempts to do that, right? So you kind of don't want to use a decision tree in production necessarily because it's so fickle, lack of a better term. You want to use something that you can trust, that's robust, that has high accuracy, but at the same time you want to be able to explain it. So that's where variable importance comes in, Shapley values come in, and so on. Really, that's the bottom line, and the bottom line is we want to keep up with new fraud behavior, right? So it's constantly being updated by the bad guys, so we want to be able to be updating our models to keep up with it. So that's all I have.
All right. Do we have a few? We have a few minutes for. Oh yeah. We have a few minutes for questions here.
So Josh will come around with the microphone, I think, because we're recording this.
Okay, thank you very much for the talk. It was very, very interesting. We will talk later. I have a couple of questions just for the time that we have. First one is how are you dealing with sensitive data? You mentioned already the GDPR regulation, so how you manage to delete users' transactions information from your model. And the second question is about the imbalanced data. As you mentioned, in real data, you always have imbalanced data. So which techniques worked the best for you? It was downsampling, upsampling, or a hybrid method? Could you please give more?
Sure. So for the first question, as far as dealing with sensitive data, I think that was almost answered in the keynote, that Delta aims to solve that question. So this is a little bit outside of my scope, because my deal is that this is the data that's been prepared for this model in production using rules. Now I'm just reusing it for machine learning. So that's kind of where I'll leave that. And the imbalanced data piece, right? I've tried a couple of things. So if you're going to downsample your data, it's quite nice. I'm a fan of downsampling because first of all, you really don't need to build a model on 2 terabytes of data. And I see a lot of that happening. Like you think you need to distribute your model because you need to build but really your yes cases are like in the thousands of that 2 terabyte data set, right? So there has to be some downsampling happening. And these models, by the way, have one of the options of the H2O models is to balance. And so you have undersampling and oversampling and a mix of the two. So one thing you can do is a grid search to try kind of several techniques. That's actually an option. But I would try undersampling to literally, to get out of that, I have billions of transactions to sift through. I need to keep all my yes cases, yes. But I don't need all my no's. I've seen stratified sampling done. So if you know there's something important about your cohorts, so you can downsample based on some factor. That's another option. And really what I've kind of seen in this experimentation is that using a log loss metric to to tune my model is going to do pretty well because I'm penalized for being wrong, not that I'm trying to maximize accuracy, right? Because maximizing accuracy is misleading. But minimizing log loss is actually a pretty good metric. Others have, there's others who like F1 statistics better. They're not here right now, so I'll say I don't like it right now. But log loss seems to be a good one. But it's always going back to looking at more than one metric and looking in the confusion matrix, because that's what's showing you what you have to actually live with. So yeah, let's talk after.
Okay, and this is actually going to have to be the last question, and then Elena will be able to take questions out
Take it
in
outside.
in the hallway. So thank you.
Thanks for the talk. Very interesting. I was thinking, so you said you're fitting your original model to the rules, and then you're updating it manually based on checking the positives that come through and updating the labels. How do you update the labels of false negatives, given that you're looking for like new fraud potentially?
Right. So there has to be a human component here. That's been my point, and that's been my experience in every organization that has a model that detects fraud. They have to have their business users or whoever they have assigned to the project, right? They have to review some number. And so the question for us, the data scientists, becomes what cases to show them. So you were asking false negatives. I want to show them a mix. I want to show them that according to my model, this is a false negative, this is a false positive, this is a model. I even show them this is a one that a model is really uncertain about. It's really the prediction probability is 0.53. So it's ending up as a yes, and it agrees with your original prediction, but really the model isn't sure. So can we look at this case too? So in my use case, right, we would flag like millions of cases a month, and then the human this is US market transactions, right? So they're in the billions a day. So when we flag millions a month, it's okay. But right, my business users, they can only handle 100 cases a month. So which 100 cases do you show them? And really that conversation then becomes, okay, you disagree with the model. Let's talk about what is it that's jumping out at you in the data, right? And they help you build new features. That was a really important component, but that you can't get around without talking to people, with just pure modeling, right? So that's a domain expertise piece that you need in this domain, in this fraud detection. Please, yeah.
Great. Thanks. So let's thank Elena one more time for her great presentation.